Let's talk about parametrized surfaces. So the definition of a parameterized surface is a function denoted by bold x from some domain in 2 dimensions called D into R3. The appropriate analogy to make here is to the definition of a parameterized curve, which is a function from an interval in 1 dimension into 3 dimensions. Here, the definition of a parameterized surface is a function bold x from a domain in R2 into R3. So here's how to visualize the notion of a parameterized surface. Let's say that we have a generic domain in 2 dimensions that looks something like this. The idea is that when we apply our function to every point in the domain, we are taking this 2-dimensional domain and contorting it with the function f and placing it inside of 3 dimensions to create some surface which is typically called S. We refer to this surface as the underlying surface of the function that defines the parametrized surface. So technically what this means is that the surface is the range of the function, which means the surface stands for all possible outputs of the function. So let's look at some examples to acquaint ourselves with this notion. So here we have a parameterization. This is a function bold x of 2 variables, s and t. And the formula for this function is a vector in R3 where the first variable is s, the first input into the function. The second output of this function is the second variable t for this function. And then the third output is s squared plus t squared, or the sum of the squares of the 2 inputs. So if you want to get an understanding of what this surface actually looks like, imagine we label the first coordinate of this output as the coordinate x. So here x is simply equal to the first input variable s. Then we label the second output variable y. So here y simply equals t. And if we label the third coordinate as z, we end up with a relationship that says z is equal to x squared plus y squared. And the idea is that the inputs going into this function all satisfy the inequalities. 0 is less than or equal to s squared plus t squared, which is less than or equal to 1 here. So what we're looking at is the relationship z is x squared plus y squared, where the variables in this definition lie in what's called the unit disk. So if we look at the relationship z equals x squared plus y squared, we realize that the underlying surface of this parameterization is a paraboloid. So the equation z equals x squared plus y squared describes exactly our paraboloid. Now, the question is, where does this particular paraboloid stop? Well, this parameterization occurs from 0 is less than or equal to s squared plus t squared, which is less than or equal to 1. And since z here is equal to s squared plus t squared, the upper bound for z is equal to 1. And this, if we're cutting off the paraboloid at z equals 1 here, sort of the upper ring of this paraboloid is the unit circle. Let's look at a slightly different example. So here we have a different parameterization. The variables for this parameterization are labeled as r and theta. And for this parameterization, we still have 3 outputs. But the first output is r times cosine theta. The second output is r times sine theta. And the third output is r squared. And this parameterization is defined where the r's range between 0 and 1, and the thetas range from 0 to 2 pi. So how might we visualize this parameterized surface? Well, again, let's label our first output as the variable x. Let's label the second output as the variable y. And with this labeling scheme, we can now label the third output, which is r squared, as z. And if we pay attention to what we're parameterizing here, or the way the parameterization works here, if x is r times cosine theta and y is r times sine theta, well, we realize that's exactly the labeling scheme for cylindrical coordinates. And in cylindrical coordinates, x squared plus y squared is equal to r squared. So once again, we actually have the relationship z is equal to x squared plus y squared. And what we realize here is that we're once again describing a paraboloid. So we again have the relationship z is equal to x squared plus y squared. The idea is that with this parametrization, we're invoking the idea of cylindrical coordinates to give an alternative parametrization of our paraboloid. So for this example, here what we're doing is we're describing the same paraboloid in cylindrical coordinates. Here the r's will range from 0 to 1, and the thetas range from 0 to 2 pi. So for instance, if we were to look at the top ring in this paraboloid, the idea is that this occurs in the upper bound for r, which is r equals 1. And when r equals 1, we're describing the unit circle once again. So in our first two examples, what we're seeing are two different parametrizations of the same surface. Our first version of this example simply described our paraboloid in rectangular coordinates, where the first two variables were just equal to the inputs into the parametrization, and then the third variable is set equal to the sum of the squares of those two inputs, which gives us the relationship z is x squared plus y squared. In our second example here, we're using the idea of cylindrical coordinates to label the first two variables r times cosine theta and r times sine theta. And then by setting the third variable equal to r squared, we're forcing the relationship z equals x squared plus y squared, which we know to describe the paraboloid. Let's look at another example. So here we have a parametrization where the input variables are theta and z. And the way that the outputs are labeled here is that the first output is 3 times cosine theta. The second output is 3 times sine theta. And the third output is equal to the input variable z. Now the input variables here have restrictions on them. Theta ranges from 0 to 2 pi, and z ranges from -1 to 1. So let's think about how the outputs are arranged here for this parametrization. So we have three outputs, 3 times cosine theta, 3 times sine theta, and then z. Well, if we look closely at these outputs, we realize that what we're describing here is a cylinder. So our first two outputs of this parametrization are 3 times cosine theta and 3 times sine theta. Well, this is exactly how cylindrical coordinates are defined when we force the radius to equal 3 here. So what we're doing is we're describing a cylinder where the radius is 3, and we're opening up about the z-axis, and the z's here range from -1 to 1. So the radius for this cylinder is equal to 3, and the height of this cylinder is 2, where the z coordinates are ranging between z equals -1 and z equals 1. So we're using, again here, the idea of cylindrical coordinates to write down a parametrization of this surface. Let's look at another example. So here we're looking at a parametrization where the input variables are phi and theta. The first output variable here is sine phi times cosine theta. The second output variable here is sine phi times sine theta. And the third output variable is cosine phi. Now, the two inputs into this parametrization are the variables phi and theta. And for this parametrization, the phi's are ranging between 0 and pi, and the thetas are ranging between 0 and 2 pi. Well, if we look at this parametrization, let's call the first output variable x, let's call the second output variable y, and let's call this third output variable z. if we look closely at how the three output variables are defined here, we realize that the three output variables satisfy the equation x squared plus y squared plus z squared equals 1. Now, we can either verify this for ourselves by simply plugging in x equals sine phi times cosine theta, y equals sine phi times sine theta, and z equals cosine phi, and verifying the equation. Or we can recognize that the way we're writing down our parameterization here is exactly what we set x, y, and z equal to in spherical coordinates when we forced rho to equal 1. Either way we look at it, the variables satisfy x squared plus y squared plus z squared equals 1. So the surface that we're describing with this parameterization is the unit sphere.